Welcome after the break to the second part of Mr. Donald Eastlake's presentation about IETF Trill.
Thank you. I'm going to launch right in here because I managed to be a little bit slow during part one, so I have one topic I didn't cover, which I'm going to do right now. It's just on peering and layering. So we sort of related to the question whether our bridges are routers. So really they're a whole new species of thing. So you have routers and bridges, you can have bridges between routers, and actually you can have like hubs and repeaters and things like that at the bottom. But Trill is really a new layer in the middle there. And you can have things ordered like this. And generally speaking in this stack, from a point of view of some box on this stack, everything below it is transparent. But everything above it sort of terminates some domain, like Trill routers and layer 3 routers terminate the spanning tree domain, and routers terminate the Trill campus. So peering, I consider two devices to peer for some particular protocol if they sort of have synchronized control states and so forth. So particular, for example, if you have something like this, routers peer if their routing protocols are sort of recognize each other or consider each other as neighbors and are in sync. And something like this, obviously the bridges, because they're lower layer, can't peer through the routers, but the routers can peer through bridges. Similarly, if you could have another layer with provider bridges at the bottom, and customer bridges can peer through provider bridges, but not vice versa, and so forth. So this is what the situation is with Trill routers. Trill routers can peer through bridges, and the bridges look kind of transparent. A bridge LAN just looks like a multi-access Ethernet link to Trill, but they can't peer through routers. So that was the section that I didn't get to cover. So this is the end of part one. So here is part two. So I'll try to go quickly through this. How many people are familiar with priority-based flow control and enhanced transmission selection? And well, I'll say a little bit about it. But the idea between what I'm calling DCP in here, that may not be the most accurate term, but what I'm calling that is the idea of trying to get lossless Ethernet by making sure you never lose traffic due to queue overflow. So you can do that with the good old Ethernet pause feature, but people don't usually enable that. It's got a lot of problems. One is it interferes with flows like TCP that depend on packet loss for flow control. It can block high priority control frames that can cause things to get screwed up in your network. And there's a congestion spreading where if a port on a bridge has been blocked or whatever by a pause, then the queue for that port quickly fills up. When that fills up, typically that switch has to send pauses out all of its other ports, and you can have this wave of spreading pauses through your network. So it's not very good. So DCB came up with two solutions. One solution isn't enough. One is the priority-based flow control and enhanced transmission selection, and the other is congestion notification. So going into the first of these, the basic idea there is to consider the different frame priorities as if they were different pipes. So PFC has a separate pause per priority. So if you do that, of course, you would not enable it. You would not enable priority-based flow control on very high priorities for your urgent frames or on any frames you're using for something like TCP, which is dependent on loss for flow control. You would only enable it on the priorities where this lossless flow is important, perhaps a couple of priorities you're using for FCOE or something like that. Enhanced transmission selection is the ability to allocate percentages of bandwidth to different priorities such that if that priority is using less than that quota, it effectively gets higher priority. And certain very high priority frames, critical control frames, are exempt from all this. So it's really the remainder of the bandwidth after you take away those very high priority frames that can be allocated. So all these kinds of things are really pretty much implemented in the port queuing logic in each box. And they make perfect sense to implement on bridges or Trill routers or end stations. Any place where you have a queue going to a port, you could have multiple queues for different priorities, you can implement these features. And my previous thing I just gave, I was showing peering between things at the same level, but peering is on a per protocol basis. In this case, the peering for this sort of thing is really different because essentially everything along the path that has a queue that might overflow needs to be part of the peering for these DCB protocols to make sure you don't have frames lost due to congestion. So answer 2 was this congestion notification, and the idea was if you were getting a queue beginning to fill up, exceeding some threshold, you send a message back to the original source of the flow, asking it to slow that flow down. And the message you send back is called a congestion notification message, and it's typically sent at priority 6. And it can have in it the source MAC and the priority of the frame, but if you want more fine-grained labeling of your flows, you can include a congestion notification tag, which is an opaque 64-bit quantity, as I recall, and that way you can have subflows and send back pressure on them separately. So this is mostly implemented in the port logic. And in Trill, if you have a CN tag, there's a draft on this that hasn't been fully approved, it goes inside the encapsulated frame. And the congestion notification message is pretty much a normal native frame, except for one curious case. So here's a Trill data frame, only in this case there's a congestion notification tag, which is in here after the VLAN tag. So there's one funny case. You can have 2 Trill routers, and you can have a bridge in between them. And by definition, sort of, that bridge is ignorant of Trill. So it might produce a congestion notification message, but that's not based on the original frame, it's based on the Trill data frame. So here's the case here, and they have this origin is sending something along here, it gets encapsulated here. When it hits this bridge doesn't understand this encapsulation, so it just sends a congestion notification message back as a native frame like this. So this R bridge just needs to do a check for congestion notification messages that are addressed to it. And if it finds one, it needs to adjust it so the congestion notification message goes back to the beginning. And there's people who believe that congestion notification won't ever work, and almost everybody believes even if you have congestion notification, you still need at least priority-based flow control to handle surges and so forth. So I don't think congestion notification is very widely implemented, but that's how it would work. So I have a section here, and it's going to talk about OAM. So this has some kind of newish material in it, including some stuff that's under development. So our bridges support SNMP, at least it says they should, and there's a MIB draft and so forth. There's BFD, and I'll talk a little bit about sort of how that's actually hooked up inside an R bridge, but that's primarily intended for use for one-hop failure detection. And I say here SNMP is primarily intended for reading configuration things, which is how most people do it. I mean, it has, you can write with it, but people don't usually do that very much. And there's additional OAM under development, which is really more, I might almost call it carrier-grade OAM, which is intended to do fault management and performance management, kind of similar to the 802.1 AG and so forth. So, and that will also actually include a facility for reporting Trill data frame errors like unknown egress nickname or TTL exhaustion and stuff like that. So the Trill OAM, all of these are OAM protocols, but Trill OAM I'm meaning a specific thing. So the Trill OAM I'm talking about now, which is under development, is really related to Trill data frame handling, whereas Trill BFD is more related to paths and flow control. The OAM messages are sent using the normal Trill routing logic over adjacencies that are part of the global topology, but on the one-hop BFD messages can be sent over links as soon as you've noticed that there's a neighbor. So the link does not have to be fully up, it doesn't have to be part of the global topology, and you can send BFD frames over it. So, and there might actually be frames, you could have a transient case like that obviously, but there might be links you would have that could persistently be in that. Let's say you have 5 equal cost links between adjacent R bridges, and you've chosen not to use link aggregation or whatever the case is, and TR1 and TR2, Trill router 1 and 2, but the logic in TR1 can only handle 4-way ECMP in Harvard. So there might be a 5th link that no data frame is going to get sent over except in case of failover, but you want to monitor it and be sure it's up so that it will be available for failover. So you can have a thing like this where, as I say, the OAM stuff, what I'm calling OAM here, is handled via the normal Trill routing engines. But BFD is specified that when BFD frames are originated, they're bound to the interfaces, the logical interfaces that Trill sees. So In this case, there's 4 links that are ECMP reachable, so they will be reachable via the OAM, which is in the process of being defined, which will have facilities for sending frames that follow the same path as data frames and so forth. But BFD could reach all of them. So this OAM that's being developed, this is the current plan for the frame format. So there will actually be a bit allocated of the reserved bits in the Trill header to indicate an OAM frame. And the first 128 bytes probably of user data will be here. So 128 bytes is about as far as the various ASIC 5-tuple hashing and other algorithms can look into a frame as a practical matter. So by using the first 128 bits of an actual data frame here, you can cause this frame to follow the same ECMP path and so forth. There'll be an ether type here, and then there's this thing labeled OAM channel, which will basically have an opcode and various TLVs and so forth for specifying what operation you want or reporting back results and things. So currently, the Trill working group is talking with 802.1 frequently, and there's a tentative plan to use 802.1 AG kind of encoding for the information here. Because there's, I mean, 802.1 allocated some opcodes and TLV values to ITU for Y1731, so maybe 802.1 Trill can get some, but that's, you know, most of the structure is kind of out over here, and the exact encoding in here is actually not critical to the functionality. So that's the OAM plan under frame under planning. This is the BFD frame format, and this has actually been approved as a standard. I mentioned there's a Trill or Arbridge channel feature where you can specify a protocol, and the Arbridge channel is intended for communication between Arbridges themselves, other than ISIS, which is a special case, not between end stations. So you have our Trill channel header, which specifies BFD, and then this BFD payload is exactly the same as it is in other protocols. One thing about the BFD standard is that the BFD standard does not define any kind of envelope. So if you want to send BFD over X, you have to define how to envelope it for X. And there's no such thing as just sending BFD itself, because you have to wrap something around it. This is how to wrap Trill around it. You can wrap IP around it. You can wrap MPLS. You can do all kinds of things. So I want to talk briefly about Trill products, what's out there. So this is pretty much all gleaned from public web pages and literature and stuff. So things like that. So for some time there have been pre-standard products. All of my slides are gleaned from those sources. Cisco Fabric Path and Brocade VCS. So Fabric Path kind of uses the Trill control plane but a different data plane, and Brocade uses the Trill data plane but a different control plane. So they're really not really exactly Trill, but you know, they have many of the same characteristics as Trill, and they are deployed. I believe there's on the order of 900 Fabric Path sites and the order of 600 Brocade sites, so perhaps around 1,500 installations of these things. But there are a number of products supported with at least the assertion that they are standard Trill. And Cisco particularly announced that the Catalyst 6500 will support what they call Open Trill next year. For some time, IBM Blade Networks has had their rack switch G8264 and had Trill support on that. Somewhat more recently, HP has announced support on their 5900 top of rack switches. Broadcom and Mellanox also have products. The Broadcom Strata XGS Trident and Switch X, they say they support Trill, and I believe them. So I believe there will be additional Trill standards supporting products announced soon. You know, you might notice that I work for Huawei, and Huawei is not listed here, but Huawei pays me to do a lot of work on Trill, so draw your own conclusions. Any box that's really using Trill for FastPath obviously has to have hardware support. So what people make silicon that will support Trill? Of course, Brocade and Cisco have their own silicon, but all the big merchant silicon manufacturers, Broadcom, Fulcrum, Marvell, and Mellanox do. Fulcrum's silicon is very flexible, so it can do lots of things. Not only is there this silicon availability, there is actually open source software implementations of Trill. There's the one which was originally with Sun Microsystems, which was acquired by Oracle and still being maintained, which is Trill for Solaris. And there's a pointer there, and there's actually a port of that to Linux in process at the National University of Science and Technology in Islamabad, Pakistan. So I gave a talk about mentioning this to an audience which had many U.S. government officials in it, and I said, you know, you might not want to use that port, but you know, it's open source, so you can look at it. I don't know, how bad could it be? Anyway, just a little bit on the status. So I mentioned some of these before. Here are published RFCs, and essentially immutable. Of course, they can always be obsoleted or replaced. And the critical one is 6325, but it is getting a little older. And there is, I mentioned earlier, this updates draft that's been fully approved, but hasn't actually been published as an RFC yet. I don't know if that's all that interesting. Here's just a list of some of the ether types that have been allocated for Trill and L2ISS. There's also an ether type allocated for more extended labeling, fine-grained labeling, more than 4,000 VLAN-like identities. And the ether type's already been allocated for that. In the interest of time, I don't really cover that in this presentation. There's a block of 16 MAC addresses, just like there's a block of 16 for bridging, which is these numbers with 00 to 0F. The block from 40 to 4F is allocated for Trill. And C0 hex is the network layer protocol identifier. And some references. Oops. And there's a URL at the bottom which uses the IETF search engine to give you a list of all of the Trill working group drafts. But it doesn't actually necessarily say what their status is in a way you can understand all that easily. There's a recent article published in the Internet Protocol Journal, which is actually published by Cisco on Trill. And there's a pointer to that. There's, I mentioned before in connection with SNMP, the Trill MIB. There's a pointer to the Trill MIB draft. And if you're interested, the original paper from 2004 by Radio Perlman that was presented to Infocom is still available, and you might be interested in it again. If you have a historic bent, you could look at that and compare what the sort of original concept was and how it's been tweaked and expanded and changed since then. So that's the end of the primary material I have, and there are backup slides here which you'll be able to see. And the very first one is I stuck in the poem for Spanning Tree, which I think probably most people have seen. So.